Hello everyone, welcome back to my channel. In this video, I'm going to explain about operational amplifier. So in my last video about introduction video of linear integrated circuits, I talked about this operational amplifier. So in this video, I'm going to explain this operational amplifier as detail. So as you can see, that is the symbol of operational amplifier, which has two inputs and one output. And in operational amplifier, one input is an inverting input and other input is a non-inverting input. And we have one single output. This is the operational amplifier symbol. So coming to the introduction. So an operational amplifier, commonly known as an op-amp, as we all know, is a two-input single output differential voltage amplifier, which is characterized by high gain, high input impedance, and low output impedance. So this operational amplifier is so-called operational amplifier because it has its origins along computers, was mainly used to perform mathematical operations. Depending on its feedback circuit and biasing, an op-amp can be made to add, subtract, multiply, divide, and interestingly even perform calculus operations like differentiation and integration also. So in today's in today's op-amps are very popular in building blocks in electronic circuits. So these op-amps are used for variety of applications such as AC and DC signal amplifications, filters, oscillators, voltage regulators, comparators, and in most of the consumer and industrial devices. So these op-amps exhibit little dependence on temperature change or manufacturing variations, so which makes them ideal building blocks in electronic circuits. So as you can see, this is the basic structure of this operational amplifier. So this operational amplifier has a differential input stage and an emitter follow output stage. So practical op-amp circuits are much more complicated than this structure of the operational amplifier. So here in this diagram, we have seen that there are two transistors Q1 and Q2 performs a differential amplifier, which where the difference input voltage is applied to the base terminals of Q1 and Q2, and the transistor Q3 operates as an emitter follower and provides low input impedance. So the output of basic op-amp circuit Vout will be given as uh, Vout is equal to VCC minus VRC minus VBE3, and Vout is equal to VCC minus IC2 RC minus VBE. As we calculated, we have this equation. By this diagram. So here we have a VRC. So VRC is the voltage across resistor RC, and VBE3 is the base emitter voltage of the transistor Q3. Uh, So in this diagram, assume this transistors Q1 and Q2 are matched transistors so that they have equal VBE levels and equal current gains. So if both transistor base terminals are connected to the ground, then the emitter currents IE1 and IE2 are equal, and both IE1 and IE2 flow through the common resistor RE. So the emitter current in this reaction will be given as this one, IE1 plus IE2 is equal to VRE by RE. And if both Q1 and Q2 bases are connected to the ground, then the equation will be 0 minus VBE minus VRE plus VEE is equal to 0. Further, we have VRE is equal to VEE minus VBE. So therefore, IE1 plus IE2 is equal to VEE minus VBE by RE. Okay, so when a positive voltage is applied to the non-inverting input terminal, then the base of Q1 is pulled up by Then the base for Q1 is pulled up by the input voltage and its emitter terminal flows the input signal. Since the Q1 and Q2 emitter are connected together, the emitter Q2 also gets pulled up by the positive input at the non-inverting terminal. So the base of the Q2 is grounded. So the positive voltage at its emitter causes a reduction in its base emitter voltage VBE2. So the reduction in the VBE2 causes the emitter current IE2 to decrease and consequently IC2 also reduced. So then it can be noted that the positive input pin, that means positive input pin will be given as a positive output, so that the name is given will be a non-inverting input terminal. Okay, so the positive here, which is the positive terminal, will be a non-inverting terminal, and the negative will be inverting terminal. So this is the basic structure of operational amplifier. So as you can see, we have some important points. So in this operational amplifier, we have to note that if an input signal is applied, if an input signal is applied to uh, either of the input terminals to other input terminal connected to the ground, so then the operation is a single-ended operation. That means in single-ended operation, a single input is applied, derives both the transistor due to the common emitter connection. So the output obtained is derived by both the collectors. Okay. Then if two inputs are applied to the two input terminals, the operation is referred to as a double-ended. So that in double-ended operation, the differences of the input applied to the two input terminals drives the transistors, and the output obtained is driven by both the collectors. Okay, for example, if the same input is applied to the both inputs, then the operation is called as a common mode. In common mode operation, the common input signal at the both input terminals are resulted in opposite signals at each collector. So these signals are cancelled, resulting in an output signal will be zero. So practically, the output signals do not completely cancel each other, and small signals are resulted to be in the input. So this is for the today's topic about this operational amplifier. Thank you.